class. Good day, good evening, good morning once again. This is another lecture in the series of Chemistry 235 for the 2021 contact section. Today we shall be discussing determination of structures of organic compounds. Remember that organic compounds can be obtained from various sources. We can get organic compound from plants and animals, and some other sources just like fungi, petroleum, and so on. Once you get an organic compound, the next thing for you is to determine what type of compound you are having with you. These are the the structures, so as to be able to determine the name. In order for you to determine the structure, you have to know what elements are present in your compounds. So for you, in the first process, in determination of the structure, is for you to carry out qualitative and quantitative analysis. Okay? The first thing you are going to do is to carry out the qualitative analysis. In most compounds or in most organic compounds, the compound will contain two or more elements from among carbon, hydrogen, oxygen, nitrogen, sulfur, excuse me, halogen, phosphorus, and all metals. Qualitative analysis will determine which elements are present in your compound. In all organic compound, carbon is present. In fact, carbon is the backbone of all organic compound. Oxygen is also present in majority of the organic compounds, and most organic compound may be found nitrogen, sulfur, and halogens. Metals, in some organic compound you may find them, and the presence or absence of any of these elements can be detected by either of the following methods. Carbon and hydrogen can be detected intimately by mixing the compound with dry cupric oxide and the mixture then heated in a tube. Carbon is oxidized in the process. Carbon will be oxidized to carbon dioxide, and this can be detected by means of calcium hydroxide solution. Remember the Milky test. Okay. Then hydrogen is also oxidized to water, and this can be detected by condensation on the cooler parts of the tube. In the case of nitrogen, halogen, and sulfur, this Lassane method is employed to detect them. Lassane method, also known as the sodium fusion test. In Lassane method, the compound is fused with metallic sodium. In this process, nitrogen is converted to sodium cyanide, halogen is converted to sodium halide, and sulfur converted to sodium sulfide. The presence of sodium cyanide, sodium halide, or sodium sulfide can be detected by inorganic qualitative methods. Phosphorus can be detected by heating the compound with fusion mixture of sodium oxide and potassium nitrate. In this process, phosphorus is converted into metallic phosphate. It is then detected by the usual inorganic test. For metals, when organic compounds contain metals are strongly heated, the organic part is burnt away, leaving behind a residue. The residue is usually oxide of the metal. In some cases, it will be the metal itself that is left as residue instead of the oxide of the metal. And this can be detected by inorganic analysis. Oxygen The presence of oxygen is usually inferred from the chemical properties of the compound. That is, whether the compound has a hydroxy functional group or carboxyl or adidic or so on. All those functional groups that has oxygen attachment will tell us that the compound contains oxygen. Oxygen is not normally, it's difficult to, the presence of oxygen is difficult to detect. So we normally infer the presence of oxygen from other tests. Now, after carrying out the qualitative analysis, you now know the elements that are present in your compound. The next step is to estimate the amount of each element present in the compound. Amount of each, how much of each element do you have in your compound? This is summed up as quantitative analysis. In quantitative analysis, the methods used in the determination of the composition by weight of an organic compound are based on simple principles. Quantitative analysis falls into three groups according to the amount of materials used for estimation. It may be macro, which require about 0.1 to 0.5 gram of materials. It may be semi-micro, which may require 20 to 50 milligram, or micro method, which will require up to 3 to 5 milligram of material. In quantitative analysis, carbon and hydrogen are estimated by burning a known weight of the compound in a current of dry oxygen. The resultant carbon dioxide and water vapor are absorbed in a proper absorbent and their weight determined, thus obtaining the weight of carbon and hydrogen present in the compound. Typical experiments used for this purpose is the Liebig's method. Okay, the amount of hydrogen and carbon is normally determined using the Liebig's method. After determining the weight, you can now use the parameter in this calculation. Let the weight of the substance, the compound itself, be x gram. The weight of water that was formed, y gram. Weight of carbon dioxide formed, z gram. We all know that in 1 mole of carbon dioxide, which is 44 gram, there is 12 gram of carbon. Okay? Therefore, z gram of carbon dioxide will contain 12 divided by 44 times z gram of carbon. That is the proportion of carbon in carbon dioxide multiplied by the weight of the carbon dioxide that was formed. Now, if you want to determine the percentage carbon that was formed, we divide the weight of carbon dioxide that is formed by the weight of the compound, then multiply by 12 over 44 times 100. That will give you the percentage of carbon. Similarly, the percentage hydrogen will be weight of water that was formed divided by the weight of the compound multiplied by 2 divided by 18. We know that the molecular weight of water is 18 and we have 2 mole of hydrogen in water. That's why you have 2 divided by 18 multiplied by 100. That will give you the percentage hydrogen. And this, it can be represented in this formula as you can see. This is for percentage carbon, and percentage hydrogen is given by this formula. In the case of nitrogen, the amount of nitrogen in the compound can be estimated generally by 2 methods. One is known as Dumas method. The other is the Jedal's method. Jedal. Okay. In Dumas method, this consists of oxidizing the compound with copper oxide and measuring the volume of nitrogen formed. Okay, that is in Dumas method. And this method is used for all organic compounds containing nitrogen. Of Jedal method, this method is suitable for estimating nitrogen in organic compounds in which nitrogen is joined to carbon and hydrogen. In which carbon is joined to, nitrogen is joined to carbon and hydrogen. Therefore, this method is generally employed for estimation of nitrogen in food, fertilizers, and agricultural products. However, the method fails in compounds containing nitrogen joined to oxygen. For example, nitro, azo, azoxy, and so on. Meaning that you cannot use Jedal method to determine nitrogen in which in compound in which nitrogen is joined to oxygen, in nitro compound, azo compound, azoxy compound, and so on. But we can use Jedal method for all other type of compounds in which nitrogen is joined to carbon and hydrogen. For oxygen, oxygen can be estimated by difference. Remember we said the other time that oxygen is difficult to determine. So we can infer the amount of oxygen present in the compound by difference. However, there are some methods that may be used in the semi-micro model. This method includes Thermulens method, Thermulens and Alois method. We can use this method to determine the amount of oxygen. Halogens. There are various methods are used for the estimation of halogens. This include Carios method, Peria and Schiff method, Stepanov method, oxygen flask method. Any of these can be used to determine the amount of halogen present in a given compound. For sulfur, sulfur is usually estimated by Carios method or Messenger's method. In these methods, a known weight of the organic substance is oxidized by some oxidizing agent, whereby sulfur changes to sulfuric acid. The sulfate ions are precipitated as barium sulfate by addition of barium chloride. And from the amount of barium sulfate that is obtained, the sulfur can be calculated, and hence we can determine the percentage sulfur in the organic compound. Phosphorus can be estimated by the Carios method. In this method, phosphoric acid is obtained, and adding magnesium mixture to the phosphoric acid obtained, magnesium ammonium phosphate is produced. The precipitated magnesium ammonium phosphate can be washed, dried, and ignited when it is converted to magnesium pyrophosphate. And from the weight of the magnesium pyrophosphate, the percentage of phosphorus in the organic compound can be determined. These are some exercises for you to practice on how to determine the amount or calculating the amount of elements that are present in a given compound. Now, once you know the amount of each element present in the compound, the next thing is to determine the empirical formula for the compound. That is also important. The empirical formula. Empirical formula of a compound is the simplest formula which expresses the relative number of atoms of constituent elements present in the molecule. And the empirical formula is calculated from the percentage composition of the elements in the compound. For example, we have this given example. We are given that the combustion of 0.202 gram of a substance gave 0.361 gram of carbon dioxide and 0.147 gram of water. What is the empirical formula of the compound? The solution is given here. In the first step, the solution consists of 3 steps. In the first step, you calculate the composition of the element present in the compound. How do you calculate the composition of the elements? We are given the amount of carbon dioxide that is obtained, 0.361, and the amount of water. We can now determine the amount of carbon that is present. And this is given, this can be calculated by dividing 12 by 44 multiplied by the amount of carbon dioxide that was obtained. And this gives us 0.0985 gram of carbon. Similarly, that of hydrogen will be 0. That of hydrogen 0.0163 gram. Then the second step is to determine the percentage composition of each of these elements. Percentage carbon will be the amount of carbon divided by the amount of the compound, okay, multiplied by 100. And this gives us 48.76%. Similarly, percentage hydrogen gives us 8.07%. When we sum up 48.76 and 8.07, we are short of, it is less than 100. Since we are not given any information of any other element that is present, we will assume that the remaining percentage is for oxygen. So we sum up that of carbon and hydrogen and take it away from 100, we give us percentage oxygen. And percentage oxygen is calculated as 43.17%. Now, having calculated the percentage composition of all the elements, we know that we have carbon, hydrogen, and oxygen. The next thing is to calculate or determine the empirical formula. This table summarizes how we can determine the empirical formula. We have the elements as listed here: carbon, hydrogen, oxygen. Then the atomic weight of each of the elements. Carbon is 12, hydrogen is 1, oxygen is 16. Then the percentage composition, as we have calculated: 48.76 for carbon, 8.07 for hydrogen, 43.17 for oxygen. Then from this information we already know, we can now determine the relative number of atoms for each element. To determine the relative number of atoms, we divide the percentage composition by the atomic weight. So for carbon, we have 48.76 divided by 12. That gives us 4.06. For hydrogen, we have 8.07 divided by 1. That gives us 8.07. And for oxygen, we have 43.17 divided by 16. And that gives us 2.7. From the relative number of atoms we have just determined, we now determine the atomic ratio. Atomic ratio for each of the elements. To determine the atomic ratio, we are going to divide the relative number of atoms of all the elements by the smallest of the relative number of atoms. If you look at it, we have for carbon is 4.06, hydrogen 8.07, oxygen 2.7. You notice that 2.7 is the smallest here. So we divide everything by 2.7. So atomic ratio here, we have 4.06 by 2.7. That gives us 1.5. For hydrogen, 8.07 divided by 2.7. That gives us 2.99. And for oxygen, we have 2.7 divided by 2.7. And that gives us 1. Now here we have fractions as our atomic ratio. We have 2.99, we have 4.5. The next thing is to multiply through. We multiply everything by a ratio so that we get a whole number. If we multiply through by 2, 1.5 by 2 will give us 3. 2.99 by 2 give us 6. And 1 by 2 give us 2. Now that gives us the simplest ratio. So the empirical formula for our compound is C3H6O2. C3H6O2. This is how we determine the empirical formula of a compound from the given information. I hope you are following me. This is how we calculate, uh, determine empirical formula. I have this question for you for practice. You can also practice what you have just discussed using this data parameter. You have to calculate the empirical formula for these compounds. Okay, these are some of the textbooks you can consult for further reading or if you want to understand better. This is the part one of the determination of the structure of organic compounds. I will be meeting you up in part two. Until then, until we meet again, I will see you.